So, okay, so let us continue. And we continue with a few remarks of general nature. So first remark concerns to generalization to multidimensional setting. So the spaces L2 of R and S of R can be generalized directly to L2 of Rn and the S of Rn. Even I would say that it's so direct that you just can modify just the definition you have seen appropriately to get them. For any and positive integer. Yeah, the second thing is about topology, or in the space of in the Schwarz space, the space S of R can be, or Rn can be provided with a topology which we will not concretize because it will take us too far otherwise. And its topological dual S prime of R n consists of so topological dual, again, it's the story of linear continuous maps from S of Rn. Consists of what called tempered distributions. If you don't know this, it's okay. But we will use it mostly in working way. I mean, often you don't need to know the general definition or formal definition, but still you can know to manipulate things. Like school people, they do not know what are the real numbers, but they can work with them. Similar thing. And the third thing is that L2 of the Hilbert space can be thought as a subspace of the space of distributions. I hope this is correct.
I'm sorry, L2 or L1?
Sorry?
I'm sorry, L2 or L1?
Of course, L1 also, but I would say the L2 also, but there is a little probability that probably there is some pathological effect where this could be happen not true. Of course, L1, it's no doubt about that, but I would put also L2. But let us put just to leave a space for a mistake. put it this way. Yeah, okay, so that was a story about the Hilbert space itself. Now the operators. One, two. Linear operators. Yeah, so definition. First part, linear operator, and linear we can drop it often if we talk too much about operators. Linear operator between two Hilbert spaces. H1 and H2. H2 denoted A from H1, H2 is a linear map. So let me put this in the quotation marks because you will see why. Is a linear map A from D of A to H2, where D of A is a dense linear subspace, vector subspace. Okay, called domain of A. Okay, this is the most general notion of a linear operator, because usually in functional analysis you often talk about just the bounded linear operators. So this is the second part. So an operator A is called bounded if its domain is the whole space, and A is continuous map, is a continuous map. So this is bounded. Then third thing is a Hermitian conjugate. Hermitian conjugate we can just say just conjugate of an operator A operator A is an operator A star which goes in the opposite way, H2 to H1, where so we have to say what's its domain. So D of A star So where f is an element of the domain of A star, if and only if the eta f A, which is a map from D of A to C, is a continuous linear functional sorry, defined by so eta f A acting on G is given by f A acted G acted upon by A scalar product. So we apply. So we take an element in the domain of A. We apply A to it. We get a vector in H2. And then we can make, with any vector, actually, we can make a scalar product. And then if this happens to be a continuous linear functional on D of A, then we say that, that f is in the domain of A star. Defined by is continuous linear functional and we A star applied to f scalar product of G is equal to that value. So here we use the Kashaev R theorem. Kashaev R. So we have a linear functional, so it can be a continuous linear functional, which can be represented through scalar product with some element, and this is the image of that f in the domain obtained by A star. Okay, then the unitary operator. What is it, unitary operator? Fourth part, an operator is A is called unitary if it is invertible and its Hermitian conjugate is its inverse. In particular, it means that it is its domain is a whole space and so on and so forth. It's bounded. Fifth part, an operator is called self-adjoint. The A is called self-adjoint. If A equal A star. So implicitly here conditions that H1 coincides with H2 and in particular the domains are the same. Okay, so that's self-adjoint. And here is an important theorem from distribution theory. Schwarz kernel theorem, which tells that for any operator, A, so let me see how I write it down. Yeah, from L2 of Rn to L2 of Rm with the domain contained in Schwarz space. There exists it's an integral kernel. Integral kernel Ka of x, y in S prime of R M. I should be careful with not to mix up M and N. I think it is. It should go like this, such that this is just a term which we use. So A acting upon on F, evaluated on X, is given by an integral Ka of xy, f of y dy, integral over Rn. Integral should be understood in the sense of evaluation on of a distribution on a test function and so on. But I will not say more on that than just this, because as I say, if we try to fulfill all the details, we will never go very far. Yeah, and here comes a little bit physics. Which is, I find always a pleasant part of functional analysis. Game of notations. Is it the third part? No, it is without number. Direct. Bracket notation. So the idea of this notation is the following. You take this word bracket, you cross out the middle word and replace it by a dash. Okay, so that's the first step. But it is a joke, of course. And then what you do, for example, you write a scalar product, which we used to write like this. And then you write it in a new way by removing this comma and putting a vertical bar. Not big deal. so far. And if you have an operator sandwiched between two vectors, yeah, this is of course now with our notation, this becomes like this. But you go a little further, you add one more vertical bar. And you go even further, so that if you have a f of x, then you write it out like x bar f. So this is not a scalar product in the sense we were talking about, but we pretend it to be a scalar product. But it is just a notation. And so we treat it as a scalar product. So for example, if we take a f of bar, so then we have a x f bar. But for scalar product, we know how to complex conjugate. So we write a f x. Right, so we have also this. And then let us take the scalar product f vertical bar g. So this is our scalar product. So let us write it explicitly. So that's a mathematically sensible thing. But now we switch in our notation here. So we get f bar x x bar g dx. And then what we do is the following. So we erase f and g here. What remains in the left-hand side? Just vertical bar. What remains in the right-hand side is this. Okay, so that's one of the properties. So you see, if in mathematical side you have to use two letters to talk about something, in this notation, you are more economical. No need for neither for f nor for g, but you say the same thing. Are there physicists in the audience? No? No physicists? Okay, then that's useful to see for you. Yeah, and now let us see what happens with the kernel. So f of x. So this is a af. And this is a x bar a bar f. And now look at what happens. So we can insert, replace this vertical bar by what stands on the right-hand side. But not to mix up with this y, we have to change the integration variable. So this becomes x a y y f dy. And then you easily recognize that this is nothing else than writing the action of the operator in terms of its integral kernel. And the integral kernel becomes a sandwich between x and y. Right? It looks funny, maybe stupid, but it works. Maybe it's a good moment to start examples. So the examples will start from Heisenberg's self-adjoint position and momentum operators. These are called Q and P. Q, but I will put often hat to not to mix up these symbols with numbers or something else. So hat will stress the fact that these are operators. And these are X from L2 of R to L2 of R. And the action is the following. So Q hat acting on F evaluated on X is equal X times F of X. And P hat F of X is equal, okay, so I have to choose a parameter called H bar, which is will be just positive real number. And this positive real number enters the definition of the operator F. This is the derivative. So that's a mathematical way of writing things. But equivalently, we can write using Dirac's notation, which looks like following. X ket, this is called ket, the other one is called bra. No, this is bra, other one is ket. So we act on bra from the right by Q and get X times X. That's what replaces this. And here, X, bra X acted upon from right by P hat is a minus I H bar d over dx bra X. So you say it's more economical. You put some extra brackets like this, but you put them anyway here also. But maybe just a usual bracket. But at least you get rid of letter F. But if we go more seriously, then of course we should talk about the domain of Q, right? And the domain of Q is, what is it? It's a set of F in L2 of R, satisfying the condition that the X times F of X is still in L2 of R. And D of P is F of X in L2 of R such that F prime of X is still in L2 of R. But here, now I'm pretending that I take elements of L2 of R in the space of distributions. But the distributions can be differentiated. So we differentiate f of x as a distribution. Then we get, so we take a distribution f of x, we take its derivative and check if it is in the L2 of R. Then that's a domain, not very pleasant thing. Then we have a Heisenberg's commutation relation. Which tells us that if we put a PQ commutator, which is by definition just the P times Q minus Q times P. And this is equal minus I H bar. But we don't write the identity. In reality, here the identity operator, so the times L2 or identity in L2 of R. But we suppress it in order it looks as nice as this. So integral kernels. And so we start from identity. So what is this? Of course, this is an integral kernel of identity. K identity of L2 of R. And we know well what is the integral kernel of the identity operator. It is something called delta of x minus y. Right? So delta of x is an element of S prime of R. Is Dirac's delta function. But coming back to mathematical terminology, it's a delta distribution. But we pretend it to be a function, because in distribution theory, you have a large class of distributions corresponding to locally integrable functions. And then the evaluation of a locally integrable function on a test function treated as a distribution is given by the integral. And then but not any distribution corresponds to a locally integrable function. But to keep uniformness of notation, we continue to write integral formulas for any distribution. And in this way, we come to Dirac delta function. But its defining property is following. So defined by delta of x integrated by f of x dx is the f of 0 for any f in the Schwarz space. And if you assume that this is true integral, then you easily will come to contradiction. So it's an impossible equality with a true integral. But as a linear functional, it's well defined. And so for distributions, you can talk about the support, and support of delta of x is just 1 point. 1 point, which means naively that the delta of x is 0 if x not equal to 0, and infinity if x equals 0. So this writing suggests that this is really not a function, because for function we don't have any meaning of taking infinite value. But there are rules of working with delta of x. What kind of rules? For example, if we take minus x, this will be the same as delta of x. Or else, or more generally, f of ax, not f, delta, is 1 over absolute value of a delta of x for any a in R non-zero. And yeah, if or even more generally, if f is a real function defined on reals, the differentiable such that f of x equals 0 implies that its derivative x not equal 0, then delta of f of x can be written as a sum over a in f minus 1 of 0, the set of zeros, 1 over f prime of a absolute value, delta of a minus x. Okay, this kind of rules of playing with this function. And of course, you use these rules just in manipulating with integrals, changing variables, all that. And so the corollary of that, of those rules, so if you integrate delta of x minus y with f of y, then you get f of x. Right? Just playing the game of you just change the variable, which is a translation, y by x. Then you will have a delta of minus y, which is delta of y, and then use the rule, and then you get that. And now, how about kq of xy? Then what we have, by definition, this is this, right? We sandwich q hat between bra and ket, with labels x and y, and then we recall the second definition of q hat. We pull out q hat to the left, which becomes x, then x bar y, and here we have a delta function. So that's the integral kernel of the position operator. And the integral kernel of the momentum operator is treated similarly, x p hat y. Then we use the rule to pull out to the left p hat, which becomes minus I h bar dx x y. So it becomes a delta function again. And so this is the derivative of the delta function. Any distribution can be is infinitely differentiable. And we have to say what is how acts delta prime where delta prime of x again it's a tempered distribution is defined by delta prime of x f of x. So we have to say how to integrate this. But we pretend that everything is just normal integrals. So we insert delta prime of x into the differential. So f of x d delta of x. Right? We know this fundamental formula, the df of x, first year analysis. And we use it for delta. Then it's an integration by parts, but let us do it formally. We put differential outside, then we correct it by subtracting delta of x df of x. Right? Here nothing is changed, just the Leibniz rule. But now we can integrate the first one using the fundamental formula for integrals. So f of x delta of x at minus infinity plus infinity minus integral delta of x f prime of x dx. Right? This is 0 because delta of x vanishes outside the origin, no contribution. And here we have a delta function without any prime, so which is a minus f of f prime of 0 for any f in S of test function, which is infinitely differentiable. So this makes perfect sense. Yeah, so that's it for today. thank you for coming. And see you next week. Each year we'll talk about similar stuff, but still as simple as this.